Hello.
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 Yeah. Yes, two are missing still now. If they will not join, then we will start from Chang, okay? Within half a minute, after half a minute. So, okay, let's start first of all. Welcome to the session on clustering method. And our first speaker is basically it is Isan, but he is not present now. So we will start from Wengzi Zhang, and her topic is K-means clustering using in dataset with missing value. So Wengzi, you have 15 minutes and you have additional 5 minutes between tag to question and transition to the next speaker. So let's start. Floor is yours, Zhang.
Oh, just to double check, do I start first? Hi, excuse me. I want to ask if I will be the person who start first.
No, you are the first person, okay? Actually, Isan is there, but he is not there. So you start, okay? In order you are the
Okay, okay, I see. Okay.
Here share option is there on the left hand side. Stop camera, below stop camera, once share option is there. You can share your screen.
Okay, I'll do it. Hello everyone. So today I will talk about the partial k-means package we developed. So our partial k-means algorithm is developed based on the k-means clustering. So here I will give you guys a quick review of what the k-means clustering is. So k-means clustering is a type of unsupervised learning. The basic idea is that we partition all the observations into k clusters. So let's say that we have k clusters, and then we will create the clusters by placing the k points, the centroids, inside the feature space. And each point in the dataset is assigned to the cluster of whichever the centroid is closest to. So, however, next, what do we do with the missing data? Unfortunately, the standard k-means algorithm fails to handle data with missing values. So what we can do with the traditional methods is that we can only modify the data sets. One common way is that we can use only the complete cases, or we can replace the missing values with means or column modes, whichever is more suitable. So next, let's see a data example that will be interesting to look at. So this House votes dataset include each of the U.S. House of Representative Congress people on the 16 key votes. The types of votes are yes, no, and unknown. Unknown is represented by the missing values here. And the 16 key votes are listed from V2 to V17 here. So next, let's pretend that we have no information on the parties. How we will discover the number of parties? Let's say that someone from Mars who don't know about the political system, and they want to see if the clustering method would find the actual parties. So next, let's choose the K. As always, choosing the number of clusters is difficult. So here, for simplicity, let's try K equals to 2 clusters for demonstration. So next, let's run our k-means algorithm to see if we can predict the correct group. First, we generate the training data set and the test set. Sorry. And then we run the training set on the partial k-means algorithm. So here we have the house model. And next, let's apply the fitted, the validation set and feed them to the assigned clusters after we updated them from the partial k-means algorithm. So next, let's assign the cluster numbers to the validation set. So it will be the house test fitted here. And this is the original class names we have for the validation set. After we run the, after we compare the testing accuracy, you can see it's 0.71875, which is not bad. Because again, here our algorithm don't know we have parties. We only have the information of the votes. So next, I will introduce the detailed algorithm inside the partial k-means. It's a really easy remedy for data sets of missing values. So here I have a simple dataset example to illustrate. Let's say our training set is comprised of this 3x3 matrix, and we initialize 2 centroids, C1 and C2. So next, let's calculate the distances. The distances is simply for the row 1, the distances will be simply the square distance from 2, 4 to 2, 3 in this case. Because here we are only calculating the partial distance, so we don't take the missing values into account. Also notice here that I divided by 2 because we want all the distances to be comparable. So we decide to divide by the number of entries in the square distance here. So when the entries is 3, we divide it by 3. So after calculating all the distances, we formulate our distance matrix. So the first column represents the square distance of each row to the C1, the centroid C1. And the second column is from each of the rows to the C2. So from here, we can see that for both row 1 and row 3, they're closer to C1. So here we will group them into our new C1 group. Finally, we will update our new centroid C1, and it will be the sum of the non-missing values divided by the number of non-missing values in each column for each entry. So for here, for the first entry, since we only have one non-missing value, so it will be simply be 2. And for the second entry, since both of them are not missing, it will be the mean of the 4 and 5. And we will complete the other entries in a similar manner. So here I have a generalization of the steps in our algorithm. The basic idea is that when calculating the square distance of each data point to the centroid, we only consider the partial distance, that is with entries of non-missing values. The partial distance is represented by di here. Di is the square distance of each row. Remember here, they will also need to divide it by the number of non-missing values. So here xi means each row, I, and the in-text index simply meaning the index of non-missing values of xi. So after calculating the distance, we will assign the cluster numbers, which is ci, to each row. And finally, we calculate the new centroid using the mean of the non-missing rows within each group. So in our partial k-means algorithm, we also have some plot features. So this plot feature helps us to visualize the influence of the number of missing values per row. And we do it by drawing the density plots of the squared distance per row between the centroids and each row. So all the distances are categorized by the number of missing values in each row. We have a second choice here. We have a histogram plot. So it is the only difference between the density and the histogram plot is that instead of the density, we have the total number of counts here. This plot is also from the Hauswolz dataset. So what we can observe here is that as the number of missing values increase per row, we can see the distribution of the distance are more spread out. That means the variance increase. So the red plot here is with 0 missing values, and for here the blue one is about 5 or 6. This feature can be important as we could inspect how the distribution of the observations or rows would change as the number of missing value changes. We can see how missing values would affect the distance to the centroids. Finally, we also compare our partial k-means algorithm with respect to the percentage of missing values in the data set. Here we are comparing our method with another method called cluster imputes. So cluster impute is another package that also runs k-means clustering with built-in missing value imputation. The dataset we are using today is IBS dataset. It's a synthetic data, so that is good because we can manipulate the data set. We can manipulate the percentage of missing to be specific. And this data set basically comprises of intakes of a different list of foods. So notice here that we know the data have two groups, the healthy group and the IDS patient groups. Since we're doing a unsupervised learning here, let's again pretend that we have no knowledge about the two groups. And as always, choosing the number of clusters is difficult. So given that we choose k equals to 2 in the IBS dataset, we want to see how well would our partial k-means predict the correct group relative to the cluster input 1. So what we do with the dataset is that we take the complete dataset and we randomly remove a certain percentage of the data points in it, and we label them as missing. And next, we run the two packages separately. So from here, we can see that when the percentage of missing we manipulate is from 10 to 30, the two methods outperform pretty well, and they have similar performance. However, as the percentage of missing dataset increase, let's say from 40 to 90, we can see here that our method have a higher accuracy over the cluster input 1. And notice here that as the percentage of missing values increase, our method has even a higher accuracy over the cluster input. So this message suggests that partial k-means would have an advantage for a larger percentage of missing values. And this could be beneficial for large sparse datasets with missing values. A great example could be datasets in the recommendation system. So for future work, I think it will be interesting to look how partial k-means would perform in datasets in the recommendation system. That's all for my today's talk. Thank you.
Thanks for nice presentation. Actually, one question is asked by team that could the partial means also deal with categorical data?
Yeah. Data.
If no, then can we proceed for next question? Able to see the question or not? Question answer.
Okay. So I see the Q&A in here. I wonder if I just tap to them or I just answer live.
No, actually you have to answer here only, live only, no problem.
Okay, let me see. Let's see. So my answer to Martin Jason would be yes, we manipulate the complete data set and made them missing. So the kind of we can manipulate a lot of kinds of data set, but here because we are doing an unsupervised learning, we so for data sets with labels on it, we will delete that row and we only take the feature rows of it.
Oh, okay. So
And
next.
and the function. Sorry.
Okay. So whether your answer complete or yes, proceed. Actually, second question asked by Corey that how would you explain the partial k-means advantage or cluster net?
Pardon, sorry, I didn't quite get that.
Actually, how would you explain the partial k-means advantage over cluster bed?
advantage. So I would say the main advantage of partial k-means over the cluster impute is based on the percentage of missing. And through my experience, I noticed that cluster imputes perform similarly with partial k-means when you have a smaller percentage of missing values, and mostly below 30 to 40. And once it's over that, partial k-means have a clear advantage over the cluster impute one. So I would say that partial k-means perform better when we have a larger percentage of missing values. Let's say 40 to 50, over 40 to 50.
Okay. So last question we will take that. What is the performance difference compared to the k-means when applied to data without missing values?
Let me see. Performance difference. When applied to data without missing value. Oh, for this, if you are mentioning the performance difference our partial k-means on dataset with and without missing values, in this case, I actually haven't tried a complete dataset for the for partial k-means, and yeah, so that's all I can say. But that's a really good question. Probably I will try that later.
Okay, thank you, Wengzi, for nice presentation. And now I would like to proceed with our second speaker, whether the Natyal is present here or not. So we will proceed with Christoph Kiefer. Okay, and our next speaker is Christoph Kiefer, and his topic for presentation is subgroup discovery in structural equation models. And Christoph, floor is now yours. You can start by sharing your slides.
Yeah, thank you. I actually have pre-recorded my talk, so I'm trying to share that.
Okay.
Just for information, I'm in the field of psychological methods, so that makes maybe explain something of the contents of the talk. So I'll try. Equation models. So what is it I am going to talk about today? Imagine you have a big data set where you are analyzing some multivariate relationships in form of a structural equation model. Quick question, can you hear something from the video?
Yes, we can hear. Yes.
So that, but because I hadn't any audio for my own video, so I wasn't sure if I...
No,
if you can hear
audio
something.
is coming. You can proceed.
But you're also in regard to yet unknown subgroups in your sample. Are there any persons for which these relationships are exceptionally different than for the rest of the sample? Then you might think about doing some exceptional model mining. Subgroup discovery in structural equation models, or shorter subgroup SAM, is an application of exceptional model mining. That is, we are using a high-dimensional covariate space to mine for subgroups with exceptional parameter constellations in a particular statistical model. This statistical model in our case is the broad class of structural equation models. And if you're not familiar with what that means, I will give you a short introduction in a minute. Basically, you can imagine them as a combination of path and measurement error models. Something very important, for example, in the social and behavioral sciences. Subgroup SAM is also the name of our R package, which I like to introduce and illustrate in this talk. At its core, it provides an interface between the widely used and powerful SAM R package Lavaan and the Python module for subgroup discovery algorithms PySubgroup via the Reticulate package. So let me show you how all of this works. And let us start with a simplistic example to explain how exceptional model mining works and how you can apply it in R. Exceptional model mining proceeds in 4 steps. First, specification of a target model to be mined. Second, the specification of the covariate space to form subgroups from. Third, definition of a measure of interestingness or exceptionality. And fourth, choice of an algorithm and its components for subgroup search. Let me illustrate these steps using the Holzinger-Swineford dataset, which is shipped with Lavaan. It contains some measures on general mental ability for students from different schools, grades, and genders. First, probably the most simple SAM that we could make the mean and variance of one observed variable. Let's take x1, which represents a measure of a visual component of mental ability. And this is one line of code in Lavaan syntax. So we are just specifying a regression of x1 on its intercept, which will give us the overall mean of x1. Here we give it a little name, m, so we can find it for later use. So we have a target model. Second, which variables should be used to form subgroups? There are not too many in the Holzinger-Swineford datasets, so we just go for school, grade, and sex. And this will lead subgroup SAM to estimate the target model within different values and combinations of these variables. For example, for all students in school A, for all students in grade 7, but also all students in grade 8 at school B, and so on. Third, the interestingness measure. This is where things get fun, because you can freely define what parts or aspects of the model are of interest for your particular mining task. So we could simply say, give us the subgroups with the highest mean on x1, and define it using another one-liner in Lavaan syntax saying, subsam qf, which is the name of our interestingness measure, is m, which we specified as the mean of x1 in the first step. That means the algorithm will return a sorted list of subgroups with those with highest means on the top. We could also get more sophisticated and search for the largest absolute deviation from the overall sample mean, which happens to be about 4.9 in this case. So here our interestingness measure would be defined with this code below. Fourth, we choose a subgroup discovery algorithm which does all of the heavy lifting for us. So this is generating subgroup variables from the covariate space, estimating the target model for each subgroup, extracting the interestingness measure, and so on. I will get into more details in a minute, but for now we just go with the defaults by using the subsam function from our package. We are passing the model syntax, the data, the covariate vector, and the interestingness measure, and this will give us the desired result. So I hope you have a good first impression of what exceptional model mining in structural equation models is, what it does, and how it can be applied using R. Now let's get a little bit more involved. Let me give you a little more background on structural equation modeling, what you can do with it, and what different kinds of interestingness measures you can build from it. As I said before, structural equation models are path models which allow for measurement error models on top. The path model part means you can have a simultaneous estimation of multiple regressions. And this is usually depicted with a kind of path diagram illustrating the multivariate relations among variables. For example, here on the left we see a multiple linear regression with a dependent variable y on the right and the predictors x on the left. And this on the right is a mediation model where we model a process where A has an effect on B and B in turn has an effect on C. This is what path models are. But the magic of SAM lies in including measurement models. So in our Holzinger-Swineford example from before, x1 is one indicator of the visual component of mental ability, and so are x2 and x3. From a psychological point of view, we would argue that mental ability is unobservable by nature. So it's not directly measurable, like, for example, height or weight of a person. But the shared variance of x1, x2, and x3 might be a measure or indication of a visual component of mental ability. And this is what we call a latent variable, which is depicted with a circle. We can use latent variables like any other variables in the SAM. So we can estimate its means, its variance, regress it on other variables, use it as a predictor, and so on. So in this next example, we specify a target model including 3 latent variables measured by the 9 variables x1 to x9. Besides the visual component, the latent variables are considered a textual and a speed component of mental ability. And of course, we assume that these components are somewhat correlated as indicated by the band errors in the diagram. This model is also known as a confirmatory factor analysis, and in Lavaan syntax it looks something like this. Now, this is a very nice example to illustrate the wide variety of interestingness measures that structural equation models offer for exceptional model mining. In the former example, we use something we call exploratory interestingness measure, which can be any function of the estimated model parameters. In that case, the subgroup-specific mean of x1 or its absolute deviation from the overall sample mean. But think of it. The model we just specified is considered to confirm a factor structure. So we might want to ask, is this factor structure confirmable for all potential subgroups? Or put differently, are particular subgroups at disadvantage for this test of mental ability, so that they would have systematically lower scores than others? And this regards the factor model as a whole, so we could define an interestingness measure accordingly by using model fit criteria. For example, a likelihood ratio test comparing the estimated model for a subgroup to the estimated model for the whole sample would provide us with valuable information on how much better or worse the model fits to a particular subgroup. In R, we can use the subsam LRT function to use a likelihood ratio test statistic as an interestingness measure. Again, you have to pass the model syntax, data, and your covariate vector, and that is it. This should take a few seconds. And again, you get this output summarizing the subgroups and their respective LRT statistic. Just on a side note, you could also use a Wald test-based interestingness measure using the subsam Wald function, but that is nothing I will get into detail here. Now I have talked a lot about how exceptional model mining works in principle and what specifics come with structural equation models. But what are actually our options regarding the subgroup discovery algorithms which make the fourth step of exceptional model mining? Which algorithms can we choose from and what do they do? Let me talk about this for the remainder of this talk. One can broadly distinguish subgroup discovery algorithms into 2 categories: exhaustive algorithms and heuristic search strategies. And the main difference between these categories is best illustrated showing some search trees. So let us assume these are all values and combinations of our covariate space. Exhaustive algorithms guarantee to visit all relevant nodes of this search tree, but each particular algorithm does that in different order. The default setting in subgroup SAM is a so-called depth-first search, which does what is shown here. It estimates the model for group A1 and then proceeds with all specializations of A1 until it cannot go deeper, and then continues with A2 and its specializations and so on. It thereby remembers which nodes it has already visited, so only visited once, which is nice. You can explicitly regress it by adding a list of subsam options to your subsam function with the algorithm argument set to DFS. If the search space is quite big, however, an exhaustive search might not be feasible. This is where a heuristic strategy comes in handy. The most used one in subgroup discovery would be beam search, and it does what is shown here. It starts off with estimating the model for all single values on the first level. Then it picks a predefined number of top subgroups and explores only their specializations. So Beam search does actually miss a lot of potential subgroups in favor of exploring only a number of promising candidates. But it's also a much faster way to explore a high-dimensional search space. It is also available in subgroup SAM by setting the algorithm argument to beam. Regardless of the overall style of the search strategy, there are more subsam options available to restrict the search space, like limiting the search depth or defining a minimal required subgroup size. Limiting the search depth means that only so and so much covariates are included into a subgroup description. The search space grows exponentially with the search depth, so it's a very powerful argument to restrict the search space. The same is true for minimal subgroup size, but this is also important from a substantive point of view. So in some cases, you may want to make sure that a subgroup is of substantial size with regard to generalizability and importance for future research. So this is my final slide. As we have seen, subgroup SAM is a four-step procedure, which starts off by specifying your structural equation model of interest and defining all the variables which go into the search space. The third and probably most fun step is the definition of an interestingness measure, which allows you to tailor the subgroup search to any particular aspect of your target model, which is relevant to you, your research and your work. Finally, you can set the specifics of your subgroup discovery algorithm and then let it run. So again, imagine you have a big data set where you are analyzing some multivariate relationships in form of a structural equation model. But you're also interested in exploring these relationships with regard to yet unknown subgroups in your sample. Are there any persons for which these relationships are exceptionally different than for the rest of the sample? Then think about using exceptional model mining or subgroup SAM in particular. For more information, you can reach out to one of these resources on the slide. And with that, thank you for your attention.
Thank you, Christoph, for a nice presentation. Any question regarding Actually, there are two persons are absent in list. One is Ishan, and another is Nadila. So whether we have to bind up the session or Yes, Christoph, one question for you from Stemman, that can you expand on how you made a rectangular pack, please? Your voice is mute. You have to unmute yourself.
Can you hear me now?
Yes, we can.
Yeah, okay. I'm not sure what you're aiming at with the question. It's I mean, Reticulate is an R package, so we're just added some Python classes to make our structural equation modeling have a Python representation of that. This is within our subgroup SAM package, and then if you're loading our package, it will automatically load Reticulate and check if everything is initialized correctly, and if not, it will tell you that it's not. And yeah, that is. And then it basically the things it does is it does the estimation of structural equation models in R, and then passes the information between Python and R back and forth.
Thank you. Another question from Steven Sam. I know how Reticulate can be used in RMD or in the R session, but how does it work inside a package? How classes are exposed to the R package?
So yeah, as I mentioned earlier, we have some Python classes which are initialized if you're loading the package. So it's nothing like in the background. I think a Reticulate and starts a Python instance, and then we are constantly passing arguments, information to the Python environment in the package. I don't know.
Okay.
Hey,
Hey,
it was here, but I didn't understand how.
they have provided one link na in mail. Whether you can join from their link or not.
Again? Hey, it was here, but I didn't.
They have provided one link na in mail. Whether you can join from their link or not.
It was here, but I didn't.
Yes, Isan has joined now. Hello, Isan. Isan, your topic is standardizing acute injury across different population, and you can start your presentation now. You have only 15 minutes. Please start as soon as possible.
Okay. Can I share my screen by any chance?
Yes, yes. In the left side, one option is the share option. You can share from there.
Okay. Thank you. Just a second.
Isan, please share your screen. Yes.
Yes, sir. Can you see that?
Yes, yes, we can see.
And can you see the RStudio console? Sir, can you see the RStudio console, Mr. Chowdhury? The RStudio console that I have?
No, you have to share your. You can do whatever you want, whether it's screen, presentation, everything. Whether you have not prepared your slide for the presentation, yeah, this you can proceed.
Okay. This you
Yeah.
can see? Okay,
Yeah.
fantastic. Okay, cool. Apologies for all of the delay in getting started. So I'm really excited to showcase some of the work we've been doing in order to standardize the definitions for acute kidney injury across different patient populations. So without further ado, I'll get started. Acute kidney injury or for a quick outline for how I roughly want to distribute it, I want to spend about 50% of the time on the methods and the results, and the other 50% of the time on the background and the conclusions. So because this is a very niche field within nephrology and within internal medicine, it's very useful to a lot of nephrologists, but a lot of times that in order to get to the use, you need to first pass professional in the fields of internal medicine, and before you can get into more specialized fields of nephrology. So the number of people this benefits from the research perspective is on the order of 100 but the number of patients that this helps is on the order of hundreds of thousands, 10 to the fifth. For example, the Mayo Clinic estimates that the prevalence of AKI is over 200,000 cases per year. So these are statistics published from Susan Titafong and colleagues over at the St. Elizabeth's Medical Center at Tufts University up in Boston. And they show that the costs of acute kidney injury are exceedingly high, both in terms of lives and dollars. The costs in terms of lives, inpatient mortality is anywhere from 1 in 4 to 1 in 5 in adults and 1 in 10 in children. Apologies, that 33.7% is not inpatient mortality, but how many patients with acute kidney injury out of the total cohort population. And sort of this third bulletin is the most interesting problem, and it's the one that we're trying to attack from the research perspective, and that's the wide variance in the incidence rates. The sort of error bounds that Susan Titafong and colleagues have estimated is between 4 and 17%, but looking in the literature, that number actually ranges anywhere from 2 to 51%. So there's quite a large variance in terms of acute kidney injury. And you can also see, based on this diagram on the left, apologies. Oh, you know what? I'm not even in. Apologies, I'm not in presentation mode. This is presentation mode, so this is a little better. As you can see from the diagram on the right, acute kidney injury occurs with many different things: cardiac surgery, sepsis, drugs, cancer. And because acute kidney injury is such an interwoven syndrome, it's hard to tease apart the underlying complexity or the underlying etiology. And to that end, that's where we're trying to step in. So what we did was we started off with the KDIGO staging criterion for acute kidney injury, which is namely looking at a small rise in creatinine in a given time frame. So 0.3 or a 50% increase in creatinine in less than 7 days or 48 hours. And what's really great about this is that it can be expressed programmatically, right, in terms of an algorithm. It's very easy to take a sliding rolling window and sort of move it across a time series and look for noticeable bumps in creatinine, or for any biomarker for that matter. So the debate about whether to use creatinine as the primary marker as opposed to an array of biomarkers is an interesting one on the basic science side, but computationally it's not as interesting to us as maybe some of the different ways you can develop these algorithms, or sort of think about acute kidney injury algorithmically. So if I were to talk with a handful of nephrologists about acute kidney injury, they would be much more interested in how the kidneys are interacting with the other organ systems, namely the heart, the lungs, the liver, et cetera, et cetera. And because that manner of thinking about kidney injury is much different than thinking about it if you're looking at the byproduct, which is this creatinine molecule. There's an interesting trade-off discussion to be had about the computational algorithmic end versus the basic science internal medicine research end. And so we're working on sort of bridging that gap. And bridging that gap as well as filling the need is what stemmed our acute kidney injury definitions. So we took the KDIGO definitions, and we created RMW, HBT, and BCI, or the rolling minimum window, the historical baseline trumping, and the baseline creatinine imputation definitions. These are sort of methods of standardizing acute kidney injury, and it has been tested with many dozens of nephrologists, nephrology personnel from all levels of training, from medical students to attending physicians to professors, across all levels of training for ease of use. So let me go and explain what each of these definitions are doing. So if you imagine that there's a creatinine time series, or a measurement of creatinine which is changing over time, and there's some admission date, and at the point of admission, the is like an area of magnified interest. Like we would love to know what's happening right as the patient is being admitted to the hospital, what exactly is going on around that vicinity. If that's the case where the rolling minimum window definition is applicable. And the idea is you take a sliding window of either 48 hours or 24 hours, or 48 hours or 172 hours, and you sort of move that along in time. And as you move that along, you look at the minimum, you keep a rolling tally of the minimum creatinine, which is why it's called hence rolling minimum, and you compare the current creatinine value to that minimum value. That's sort of how we look at deltas across times, and that's the sort of most straightforward implementation. The next is called the historical baseline trumping definition, or the HBT definition. Excuse me. And the idea is to take the median of the outpatient creatinine values from 365 to 7 days prior to admission and call that the historical baseline creatinine. That historical baseline creatinine is what the current creatinine is compared to, rather than the local minimum values as your time window is rolling forward. Finally, we have the baseline creatinine imputation definition, which is a method of imputing creatinine based on glomerular filtration rate, which is another nephrology speak for how well are your kidneys doing, how well are your specifically how well are they filtering the kidney. The nephron unit is sort of broken into the glomerulus and then the proximal convoluted tubule, a loop of Henle, and then distal convoluted tubule. How well is the initial segment of that nephron able to filter? And by using a value of 75, we can impute the creatinine value, and that imputation is sort of an overestimate for what the actual creatinine value should be. And there are a lot of people who are sort of doing tiny perturbations to this equation to see how well you can then predict creatinine curves, or based on like glomerular filtration rate and vice versa. But for the sake of baseline creatinine imputation, we merely use a value of 75 and impute a serum creatinine based on that. So it's a little dense, and it's a little technical, but are there any questions at this point? Cool. I will just keep going then. So we created this tool, and it's called the AKI Flagger, and I'm having a little bit of trouble showing the R Studio console, but it's very straightforward. It's like a library, just like any other package. You can download it from CRAN. You do library AKI Flagger, and I'll just type that in the chat. Is the name of the R library, and then the functionality and the documentation is all there, and the 4 columns that are necessary for minimal input are the patient ID, the timestamp, so at what point was the creatinine measurement taken, whether the actual creatinine measurement, the value, and then whether that measurement was taken in an inpatient or an outpatient setting. And the reason that matters is just because in a hospitalized setting, the types of hemodynamic fluctuations are different than in an outpatient setting. Okay, all that aside, this is the main point. It's a chaotic system, right? Very subtle differences in the initial conditions or how you define acute kidney injury have massive differences on which patient populations are being captured. And so you can see that these numbers vary on the order of thousands, and I should have written it here, but N is equal to 40,000 in this case, or there's 40,000 patients in our cohort, and you can see that there's about a variance of 2,000 patients, 2 to 3,000 patients. So we're looking at it anywhere from a 10% discrepancy, right? Order of magnitude, 10%, in terms of which patients are being captured by which definition, which actually has a tremendous amount implications for nephrology management and how nephrology professionals are managing the disease, right? If a patient has acute kidney injury, that's an entirely different course of action that needs to be taken than if a patient doesn't have acute kidney injury. So sort of have all these various metrics of interest, deaths, dialysis, length of stay, to sort of compare how different definitions are comparing. And sort of the most iconic, the most emblematic difference is as you go down in terms of definitions, you can see that the baseline creatinine imputation has a significantly quicker time to AKI. And that means that the sort of reasoning, the way you should think about it is, if I am looking at values in my locality, then I'm using the rolling minimum window. But until I have two measurements, I'm not able to make that, which means because I have to wait longer to get the measurements, because we have longer to take the measurements, it takes longer to detect the AKI. So as you go, but for the imputation definitions and for the trumping definition, you don't need apologies, you don't need prior information. Oh, I mean, you're using prior information, but other types of prior information, namely age, sex, demographic information, not the actual lab values. And so the diagnosis can be made a lot quicker. So even though the sensitivity and specificity, namely concepts which I may, if the audience is not familiar with, they're just ways of accounting for false positives, false negatives, true positives in the accuracy, precision measurements. I'm sorry, I realize I'm running low on time, but you can do a bunch of very cool statistical analyses on it and get some pretty color plots. And the color plots tell you something about which definition you should use in which case. But to the audience that I'm speaking to, that is a little out of the scope, because it may be the case, for example, that an ICU patient would prefer, or in an ICU setting, you'd prefer a rolling minimum window definition, versus in a post-cardiac surgery patient, you would prefer to just impute their creatinine based on demographic information. Because you would maybe say, okay, I'm going to disregard the fluctuations that I'm seeing in the creatinine in my locality because I know this patient just had cardiac surgery, or a slew of other things. And so it's very case by case, but it is a good way of partitioning the space such that you we can start to make a sort of standardized consensus notion for what acute kidney injury is, and that's really our goal. So all of this stuff is a little caviar, but thank you guys very much for listening to my talk. And if you have any more questions, please feel free to email myself at is439@yale.edu, or my brilliant PI at francis.p.wilson@yale.edu. Thank you very much.
Thank you, Sean, for very energetic and informative talk. If any question is there, then we can proceed. Otherwise, session will going to end very soon. If no question, then we wind up the session. Thank you, Sean. Thank you, everyone, to join
Thank
the
you very
session.
much.
Christoph Wengzi, thank you. So we can now leave the session.